Assalamualaikum and a very good day to Dr. Akmal and to all viewers. Today, me myself, Muhammad Ali Naufal, alongside my group members from Group 2, will be presenting the topic Copper Aluminium Alloy. So here are the group members of Group 2. So we will begin first with the introduction. So what is aluminium and what is copper? So aluminium, which is Al, is a soft lightweight silvery metal, which is placed in the group 13 in the periodic table. While for copper, it is an extremely ductile material that is unusually a good conductor of electricity and heat. So copper is placed in the group 11, which having one valence electron in the periodic table. Since the beginning of the aluminium industry, copper has been the most common alloying element. Copper-aluminium alloys are commonly known as aluminium bronze. The aluminium bronze are a family of copper-based alloys with exceptional mechanical and chemical properties. They have excellent strength compared to those low alloy steels. So you can see on the right hand side is the figure of the aluminium copper alloy. So it is a reddish metallic solid metal. As we can see here is the properties of copper aluminium alloy. The melting point is very high, as it is high as 1047 degrees Celsius. The value of tensile and yield strength is also high, as each has the value of 690 megapascal and 380 megapascal respectively. The shear modulus for this alloy to be recorded as 42.3 gigapascal. So that is all for the introduction of this alloy. We will be moving on to the application where what is aluminium copper alloy is used for.
Application. There are a lot of examples of application on car and aluminum. One of them is marine boats. It is 89% car, 1% iron, and 10% aluminum. They are used in all mechanical systems to control the fluid flow through the pipes. My second example on car aluminum application is gears. It is 11% aluminum and 89% car. They are used in transfer motion and tension between the mechanical parts. Also, gear can be changed the direction of the rhythm by increasing or decreasing the output speed and tension.
Hello everyone, I'm Veronesh Sharma here. So now I will explain about the solidification process of the 3% copper and 97% aluminium alloy. The aluminium 3% copper alloy is hypothetic as its composition lies on the left side of the eutectic composition. So as you can refer to the phase diagram, you can see the eutectic point at 32.7. So the 3% copper lies on the left side of the utility composition. During the solidification process, the liquid aluminum will start to decrease in temperature, and as the temperature decreases, the liquid aluminum will go through the liquidus line, as you can see the phase diagram, into two-phase alpha plus liquid region. As the temperature drops further, it will pass through the solidus line just below the 660.452 degrees Celsius, and it will pass through the solidus line where all the remaining liquid has turned into solid alpha. So, as the temperature decreased continuously, it will pass through the solvers line. Solvers line just on the 500 degrees Celsius. It will pass through the solvers line where the beta is no longer stable in the material and starts to precipitate out into second phase. This will cause the formation of beta at the ground boundary. Next, Next, we can see the microstructure of solidification process. These are the microstructures, as you can see, and labeled accordingly on the phase diagram 1, 2, and 3, 4. So next will be the cooling curve of solidification process, and you can see there is liquid plus alpha, alpha and alpha plus beta. Next is the composition of the amount of phase at temperature 500 degrees Celsius. The calculation are made, and as you can see, the composition of alpha is 90.91% and the composition of beta is 9.09%. That's all.
Assalamualaikum and hello to all. My name is Nurul Azlina binti Zakaria. I will present about aluminium that contain 20% of copper and one of the method to improving material properties of copper aluminium alloy. As you can see at the slide, is a phase diagram of copper and aluminium alloy. At 20% of copper, alloy is a eutectic as its alloy composition placed at the left of the eutectic point. The liquid alloy initially contained a higher percentage of aluminium than that corresponding to the eutectic composition. Therefore, the primary solid phase that formed is alpha. Formation of the alpha phase deplete the remaining liquid in aluminium and liquid composition shift toward the eutectic composition. When the composition reaches eutectic, the remaining liquid follow the eutectic reaction. Then, at room temperature, the microstructure consists of primary alpha, dendrite surrounded by the finally divided eutectic mixture of two solid phase, which is alpha plus theta. The slide shows the microstructure of the solidification process and the cooling curve. As you can see the cooling curve, at the beginning, it is a liquid region, but the temperature is 600 Celsius. The liquid enter the new phase, which is liquid plus alpha region. So, the slide show the how to calculate the composition and the amount of the phase of the copper and aluminium alloy at the temperature of 500 Celsius.
Now we will discuss a point in the phase diagram where it is a point at 33% of copper and 67% of aluminium. So the phase that's been identified at 33% of copper is a eutectic reaction, and during a eutectic reaction, a liquid changes into two solid phases as it cools at the same time. So the reaction at 33% of copper can be shown as liquid turning into alpha plus theta. So as you can see in the diagram on the right hand side, you can see the small yellow circle. So that indicates the eutectic point, where this shows that eutectic reaction occurs at 33% of copper. Next is the transformation during solidification process. So to make it easier, you can also refer to the cooling curve or the solidification process. So you can see in the first line, there's the liquid mixture cooling. So in this phase from 700 degrees Celsius to 548.2 degrees Celsius, it was only in a liquid state. So after that, which is the line, the constant line, which is the isothermal solidification of eutectic composition, which is at 548.2 degrees Celsius, which indicates is the eutectic temperature. So at this time, all three phases will all be present, which the liquid, the alpha, and also the theta. So as you can see, there's a constant line. So actually, it will take some time from the liquid to change into solid. So that's why there's a constant line where it will take time to change into the solid phase. And lastly, the solid mixture freezing line, where it is already in solid phase, where only alpha and theta will be present. So this is the microstructure of the solidification process. So as you can see in the diagram, the phase diagram, I've marked 3 points. So in the first point is where all liquid is present, where it is at liquid state. And at the second point is where the laminar structure starts to form, where you can see there's liquid and also alpha and theta. And lastly, where the laminar structure completely formed at point 3, where there's no more liquid, where only alpha and theta present at the third point. So here is the composition and the amount of phase at one temperature. So in this situation, we'll be taking 400 degrees Celsius as our example. So in the phase diagram, F mark the distance between the alloy phase to the solid and to the liquid phase. So from A is where the alloy to the liquid phase, while for B is from the alloy to the solid phase. So on the right hand side, it is calculated that the composition of alpha is as much as 39.58% and the composition of theta is as much as 60.42%. So that is all from me for now. So we will be moving to the next point in the phase diagram. Thank you.
Here is the phase diagram for 45 weight% of copper in aluminum copper alloy. In yellow mark represent the region for 45 weight% of copper in phase diagram. So these are the process for transformation during the solidification process. So when at first it liquid solution form of the alloy. So when the temperature is cooling down and the temperature reach at 590 degree 90.5 degrees Celsius, the primary theta will form in the liquid. So and primary theta will grow larger until the temperature reach at eutectoid temperature. When the temperature reach at eutectoid temperature, the growth of the primary theta will stop and the liquid will transfer to and make the structure of lamellar structure. And this is the isothermal process, because in that point the temperature will be hold until the liquid fully converted into lamellar structure. And here there will be eutectoid reaction. Liquid will form eutectoid theta and eutectoid alpha. That means it will form lamellar microstructure, and when the temperature cross the eutectoid temperature, liquid fully form into lamellar microstructure and the large primary theta will surrounded by lamella. And here we can see at point 1 there will all liquid, and point 2 there will be primary theta will be grown in liquid, and point number 3 the primary theta will be grow large, and some liquid will also transform into lamellar structure. And when it crosses the eutectoid temperature, that means it point 4 the whole liquid will transfer into lamellar structure, and the large primary theta will surrounded by lamellar microstructure. And in here lamellar microstructure it will create by eutectoid theta and eutectoid alpha. These are the cooling curve. At 590.5 degrees Celsius primary theta begin, and 548.2 degrees Celsius primary theta end. And in this is the isothermal process. Liquid transfer into lamellar microstructure, that means liquid transfer into eutectoid alpha and eutectoid theta, and after that it will become solid. And these are the chemical composition of at 45 weight% of aluminum copper alloy. Here overall composition is 45 weight%, and composition of alpha is 5 weight% of copper, and composition of theta is equal 54.5 weight% of copper, and amount of alpha is 89.9%, amount of theta is 10.11%.
Hi, now we will discuss on the copper aluminum alloy with the composition of 53% copper and the 47% of aluminum. This is the microstructure cache of the copper aluminum alloy. The point 1 is when the temperature is higher than 591 degrees Celsius, the alloy is in a liquid phase. And then when the point begin at the temperature of 591 degrees Celsius, the alloy slowly begins to change the phase as the primary theta begins to form at the center of the microstructure. And then at the point 3, with the temperature of 550 degrees Celsius, the solid structure of the primary theta will completely form, and it can be seen at the end of the cooling phase. Now move on to the cooling curves of the solidification of the copper aluminiums with the composition of 53% of copper. As the temperature moving down to the 591 degrees Celsius, the alloy is still in the liquid phase, and then as it arrives at the 591 degrees Celsius temperature, the primary data will begins to crystallize, and then the process will go and end at the temperature of 585 degrees Celsius, and then it will form the solid data structure of the alloy. And then this is the composition and amount of phase at the 550 degrees Celsius. The mass of alpha found is 50%, and the mass of the theta is the same at the 50%. That's all for me. Thank you.
Isothermal reaction. It is reaction in which the temperature remains constant through the time of the reaction. At this reaction, the change in temperature equals zero. This is shown in the figure mentioned phase diagram of aluminium carbon alloy. In thermostatic solution, it is a type of substantial solid solution in which there is high amount of solute element. Solid solution. A solid solution is a type of a solution which has uniform composition of two crystalline solid that share the common crystal structure. Seventy percent of carbon alloy belong to the high protectic alloy of carbon and aluminum, as it can be seen from the figure phase diagram. The alloy lies at the right side of the protected reaction. Liquid cooling. At this stage of solidification, the liquid aluminum temperature begins to drop slowly, its energy decreasing slowly, and it becomes stable, and its temperature begins to become in the state of equilibrium. Freezing begins. At the point the freezing of the liquid aluminum starts, its cooling starts from the wall of the mold. Freezing complete. At this point, the solid formation is complete and its temperature reaching the room temperature. Here is the sketch microsection of solidification process and sketching of the cooling curve of solidification process. And at the temperature of 550, you're gonna get 43.1% and 56.8%.
Next, I will talk about cold working as one of the methods to improve the material properties. Cold working is a metalworking process where metals are reshaped or deformed below its recrystallization temperature or at room temperature. Cold working consists of three methods. Firstly, rolling. Rolling is a method that is passing between two rollers which exert high compressive force on metal and reducing the thickness of that properties. Next is forging. Forging is deform a single piece of metal by continuous squeezing and give preferred structure. Next is about the drawing process. Drawing process is done through tensile force where metal is deformed by pulling through a die. In cold working process, defect density increases. Due to the increment of dislocation density, it creates obstacle against the dislocation motion. As you can see in the picture on your right, the cold working process. So that means it receives further dislocation, which means it increases the yield strength of that material. Therefore, the material becomes harder and more brittle. Pure aluminum yield strength at room temperature is 30 megapascal where it is fully cold-working state, and the yield strength can be as high as 165 megapascal. The yield strength increases with the percentage of cold working. So finally, cold working uses in several engineering applications such as aviation, aluminium, steel, automobile, and etc. And aluminium sheets can be produced by cold working. As you can see on your right, this is the picture of cold working aluminium alloys. That's all.
Edge hardening is one of the method for improving the material properties of aluminum copper alloy. Actually, it is one kind of quenching process, but it takes time for the improvement to make material hard. So in this process, at first the heating process will start below the melting temperature. That means it will remain in the solid phase region, and after the heating, then it start to cool, rapidly cool. When the temperature below down from surface temperature, the composition of copper will be increased, then the equilibrium state. So the excess copper will create precipitate, which is copper aluminum 2, and this precipitate will make obstacle for deformation motion, and which will make material harder. When the temperature reach a quenching temperature, and the temperature will be hold at time, and the precipitate will increase in the alpha region by time, and here the growth is lower, and here the grain growth is lower, but the nucleation is fast, so the grain size is small, and it will create a large obstacle to deformation motion, and it will make material harder. So in engineering and industrial application, the harder material will produce by this method, such as gear shaft, propeller, etc.
Here are some methods of improving cuprum aluminum alloy. The process is called annealing process. Annealing is a treatment process that occurs after the deformation of metal. This process restores the early value of mechanical property of cold work material. At this process, yield strength of aluminium copper alloy can be decreased and recreate alloy more ductile. There are several processes in annealing, which are recovery, recrystallization, and grain growth. Recovery is the first process in annealing. In that region, deformation aluminum alloy can reduce the stored energy by removing defect, and aluminium cuprum alloy will be heated until temperature reach 1247 degrees Fahrenheit. Next process is recrystallization. Recrystallization is occur in aluminium copper alloy at temperature 1247 degrees Fahrenheit. This annealing temperature will keep constant until the new grain crystallization fully completely, and new set of strain-free grain has same dimension in all direction at inside and at grain boundary. Last process is grain growth. Grain growth occur by the migration of grain boundary. In annealing, alloy cool down in room temperature slowly. However, newborn grain get enough time to grow up and grain will be larger. Move to the next slide is example annealing in engineering and industrial application. Annealing aluminium becomes softened so that this process is used for aluminium cord. Other that, heat sink for cooling CPU and graphite processor. Aluminium is the key material because of it has heavy thermal conductivity. After annealing, aluminium can be given any shape. So, in industrial, several kinds of application to obtain desired shape.
In conclusion, there are several methods for improving the materials properties of aluminum copper alloy, such as annealing, edge hardening or known as quenching, and also cold working. And to improve the microstructure procedures can give many benefits to ensuring the safety, to obtain the desired shape, and as well as increasing the material strength to resist the deformation. Some method can be used to analyze the copper aluminum alloy phase diagram. It includes the transformation of phases during the solidification process, and reading the cooling curves, and also identifying the number and composition of phases using a tie line, and also by calculating the phase fraction using the Lever rules.
With that, that's the end of our group presentation. Thank you.